I can speak with this, and whoever wants to speak can. Okay. So I was just thinking I can lay out a few of the open questions, and then we can take it depending on where people's interests are. There is so I think there's the AMPS arguments, the further AMPS argument. That's one thing which I think we should discuss, which I'll call AMPS 2, 3, and 4. Okay, so there are many AMPS arguments, and there are further versions of the AMPS arguments that they've made. So that's something I think to discuss. There is, I think, one question which Ashok mentioned, which I think we should really discuss, which is this issue of the entanglement entropy and what significance that has. Then I think there are some issues about the Maldacena-Susskind, solution, and that what significance it has for flat space. And I think then there are maybe something else which I think we should discuss, which. Okay, are there any other topics, people think we should discuss? We can add them to the list now and go through them one by one. So anything else, you'd like to talk about related to today morning sessions, we can add here, and something you were not comfortable with or wanted to discuss or felt would be a way out. Okay. Maybe I'll link it here. Okay. Anything else? Post-selection paper? Not as far as I know. I don't know anything about it also myself. He's doing quantum error correction, as Dilip. Yes, the Verlinde paper. There's a paper, there's a proposal that post-selection helps you avoid some of this. You have post-selection quantum mechanics. You have impose a condition on the final state. I don't understand anything about that. So tomorrow we'll have some discussion on quantum information theory. There's an error correction, and maybe we can combine. There's a second discussion session, so we can. Right, there are two discussion sessions. There's one today and there's one tomorrow. Okay, so one of the things I could do is I could try and summarize some of the other arguments of AMPS if people are interested, because there are multiple AMPS arguments. So we can do that, or we can address some of the other questions before, which really depends on how people would like to take it from here.
Yeah, basically it's a general, unhappiness about the fact that the state, of the collapsing star, okay, that is not taken into account, with any kind of explicit stuff. For example, when we compute the D1, D5 black hole and compute Hawking radiation from there, etc. So we know exactly what the material description of that state is, and maybe here one can consider some DD bar rings collapsing or something, and some radiation coming out there. So clearly, it would appear that that state is not like a product of a black hole state times some zero out, zero in, and going into something, and in which the entanglement is only happening among the phi modes, and yeah, well, there's not much more to say. It's just that yeah. Yeah. Well, yes. Yeah. Well, so yeah, it's that kind of thing. I mean, for example, that you can. So if you have so basically, so this kind of a system, you have some left moving and right moving modes moving on something. Like that. This is the state. And so then you evolve this kind of a state with a Hamiltonian which has these guys. So there is some A dagger, A tilde dagger, and some graviton. Such terms. Yeah. Oh. This. Oh, it's not on. Is it on now? I don't know what. I see. Yeah.
I thought you were leading to the opposite. Namely, I thought you were setting up the problem very nicely as follows. The theory of the stretched horizon is, let's look at it from really far away. Okay?
Right.
If you look at it from really far away, then the theory of this, which describes the dynamics of the stretched horizon is your D1, D5 system.
Right.
So now we have two descriptions. Either you use the bulk interior,
right,
not this artificial D1, D5 at the stretched horizon.
Right.
Then it would seem matter falls in, and okay, Hawking tells us that thermal radiation comes out, but where are the corrections?
Right.
Or you say, I'm going to be someone very far away, and I'll say there's a stretched horizon. Now, it's clear that the evolution is unitary, and even though it might look approximately like the thing is thermal, you know that in the end it will get unitarized, right? So, but if the bulk is dual to the boundary, the same thing must be happening in the bulk as well. How does it happen? Through corrections.
That's right.
That's the question.
Yeah.
You know how those corrections have to be e to the minus n. I mean, you don't expect that the semi-classical computation will see those corrections. From the bulk perspective, if the bulk description is at least accurate to some extent, then those corrections are very small. They're smaller than any power of s provided in the.
But are the corrections e to the minus s from the point of view of the D1, D5 system?
Yeah. Let me tell you one.
The information is in that.
Yeah. So let me tell you one concrete calculation. So here I have let's say this black hole, and let me call this guy.
So you make it yours by hitting
this is my initial state, and the process that I have in mind is something in which one quanta each of this as well as this, okay, get converted into a graviton quantum. So I have this and I have this, okay, that's the process. And so you evolve this in time and do time dependent perturbation theory. So you will find that it will be this guy whatever the original fellow plus some amplitude times n omega minus 1 in a particular mode, this minus 1 with some delta, Kronecker delta, and some one quantum of the alpha that has come up, and so on. You can explicitly compute this in the field theory is no big deal at all. And of course, there is important interference effect between these guys. That all can be done, computed. So furthermore, I mean, what I'm saying is that, of course, when we computed this stuff to explain, so this is like some amplitude for emitting a closed string quantum or something like that. We immediately did mod square of this one, okay. But indeed, there is important information here about before doing the mod square. Furthermore, not only did we do mod square, okay, we immediately summed over all possible channels the states that are here, okay. Only then, okay, you got the Hawking radiation. Before that, you didn't get Hawking radiation. In particular, the stuff that we got here is something that explicitly for a particular mode, let me call that mode, okay. So it's like that. This is what the amplitude was, in fact. So this amplitude actually carries information, okay, about the microstate, okay, for a particular mode only. If my detector, okay, is a detector for a graviton of the kind twice omega bar, then it carries information about the occupation number of that state. But it does carry something.
I think the distinction between this model and the other cases, you don't have the analog of the C's in this model. Where's the Hawking quantization?
Good question. So I would like to say that the C modes, okay, are describing something of this de-excitation. So after all, the C modes are going in. Okay.
One second. Why do you say that? There's a Poincaré horizon, right? In the Poincaré.
No, I'm saying.
Wait. But this is a dual description of a geometry. Sure. The geometry has a horizon. That's the whole point.
In the CFT.
No, but that's the whole point. I mean, I completely agree with that. But in this model, you can compute the corrections to Hawking evaporation.
You have that.
I mean, suppose you do everything here, you can never be sure that dual geometry is full. Who tells you that dual geometry?
Can I give you an even simpler model with this?
Yes.
You have no directions.
Okay.
Very simple model which has corrections talking to it.
Yes.
It's the following model. It's a spin chain. So just think of n spins. Okay, so these are n spins. And my model of Hawking evaporation is one by one the spins break off. So this spin chain has 2 to the n states. It has states that go from 0, let me call 1 to be the state where all of them are up.
Right.
2 is the state where the last one is down. Then 3 is the state. So I can order all the states up to 2 to the n.
Good. Yeah.
Let me take a state which looks like some complicated linear.
Correct. Good.
And my model of Hawking evaporation is that the spins are breaking up one by one. If I look at the density matrix of any individual spin, let's say I look at rho 1, the density matrix looks like the thermal density matrix, there's no temperature here, like the identity matrix, the maximum entanglement matrix, with corrections that are suppressed by 2 to the minus n by 2. So I look at this, it looks like it's a thermal matrix, except that corrections are exponentially small. So this is explicitly unitary evolution. So once everything is evaporated, I've come back to it. So clearly, there's unitary evolution in which if I look at a small subset of states, or any subset of states, it looks like it's completely a curve. What's missing in this model is where are the C's? This is my B model estimated. I can make a model of harmonic oscillators if you like. So this is a model that has a strip of everything except the information theory, which is so this let me call this n omega. This could be a model of n omega. I can give you a harmonic oscillator to really give you. So this looks thermal. All these powers look thermal. Rho 2 looks thermal. All these density matrices look thermal. But there's explicitly unitary evolution. In this, there's no analog of the C's.
Which is again you have n spins.
I have n spins. They're 2 to the n states of these n spins, which are labeled in some way. I've taken some arbitrary superposition with some coefficient Ci. Now, my model of Hawking evaporation is much simpler than Gautam's model also. There's no dynamics, just the spins break off on them. Okay. So we go from one box to the other box. Okay. Clearly, this process is unitary. Yet all the spins have come to this box. So whatever state there was, the same state. Okay. Now let me look at the first spin or the second spin or some number of spins. It's easy to show that the density matrix of the first spin is exactly the identity matrix, half of the identity matrix. Up to with corrections that are. So if I look at the entanglement network.
In some particular state, is it? Or sorry.
In generics.
In a generic.
Generic state, you take to the R. These corrections depend on which state you
Yeah, that will
the
happen.
entanglement network of the spin is solved. Absolutely. I can do this for 2 spins, 3 spins. As long as I don't measure very fine correlations, I'll keep seeing it completely fine. But the information is hidden very, very fine correlations. So this is an example of the system you're talking about. It's like that. There is information here, but when you look at one bit, it looks thermal.
Yes, but the point is that I think that's the point you were making also, that I should keep track of these correlations, shouldn't
I
I?
should keep track of the correlations, but this is the point that Polchinski and others and Mathur and so on are making is that very importantly in these models you have to find a description of this P. What's the bit that falls inside that maximally entangled with this guy?
But for the limited question, at what order in terms of bulk quantities do the corrections come in? Let's say Hawking's calculation is the right answer in some semi-classical, suppose, approximation. Are the corrections 1 over h bar? Are they e to the minus 1 over h bar? Probably e to the minus.
But the corrections are 1 by s, probably, but for Hawking's computation, but the information is e to the minus s. The corrections
are
one
just
by
order, next order in h bar.
But the information is probably sitting at e to the minus.
So what does that mean? I mean, the correlators start getting, let's say, let me put it like this. You measure some local entanglement to leading order is thermal. It starts getting corrected, keeping the size of the leading order of interest in h bar. I think that's true. But the correction to each order in h bar is universal. Is e to the minus.
So the correction, this would be the picture, right? That you have a collapsing matter. So I weight log s. So there's no head theorem that tells me everything died off at e to the minus w. W is some coefficient that's calculated. So I wait for some time and I fall in here. This guy doesn't know, the information that this guy receives from this guy is e to the minus s. So
It's not obvious because the modes which are going to finally make their way out are going to encounter that stuff in between.
Well, there's no information in this part about this matter, right?
How do you know a mode which is going to make its way out, skirting the horizon, sees both things before it goes up?
Well, okay, the
And there's a
semi-classical
transline
geometry is universal up to beyond, if I wait for some time, which goes like k log s, the geometry is universal up to
that's
R
not
1
enough.
times the k.
You are interested in the state of a mode which makes it to scribe class. That mode, as it propagates, has Transplanckian collisions with all of this stuff. I know it's empty, but if you're really trying to solve for that mode, it does have huge interactions.
Can't we just say that, can't we do the Hawking computation in local sense by just doing it here?
What does that mean? I'm trying to understand the state of scribe plus and relate it to scribe minus.
I feel that, but so there's a very non-local map between how that state of scribe plus gets related to scribe minus. But all I'm saying is that the geometry here semi-classically doesn't have any information about the embodied matter up to any power 1 by s to the k. So any computation that you do, I think that locally depends only on the geometry. And I think you can derive Hawking's results by just looking at one path. I don't think you need to
Yeah, but for the correction, I thought the question was,
Even the corrections you can draw it, right? Because it's not really exactly flat space with their curvature things that are suggested by 1 over x. Those that will also give you corrections.
At least to me, it's not entirely obvious that the leading corrections are of that local type. I mean, no, okay. All right.
Then I can wait as long as you like, right? So that past is gone. You're saying the corrections don't come from there at all? Why do I have to derive
the large n when the maximally twisted sector is being discussed.
Right.
Otherwise, we have all types of stuff there. Actually.
Yeah. Yeah.
All the cycles of the
Yeah. So even that's true. Yeah. I mean, even this is a simplified result.
Isn't this been done at weak coupling?
At weak coupling. I was just going to say that this is of course done at weak coupling.
To find the C mode because the dual geometry doesn't have a.
It doesn't have. It hasn't formed. It hasn't collapsed into. Yeah. But I'm saying that to say that the entanglement between the big thing and the small thing disappears by sort of cranking up the coupling. I mean, it's not clear what the mechanism of that is. I agree that this computation has to be done at strong coupling, and but maybe there are arguments of the kind Subrat is saying that.
This argument is based usually on this inner mode, right?
Right.
Yeah, very good.
Absolutely.
You will never find any C in any weak coupling.
That's right. So maybe that is the issue of finding the C modes using ADS CFT inside CFT, and weak coupling CFT of course can never see these. Yeah.
The AMPS arguments are generally trying to argue that you cannot find a C operator in the C. And actually, I agree with them in the extent that I think you cannot find a state-independent C operator in CFT, but I think you can find a state-dependent operator in CFT. That's true.
Like that Maldasena's capacitor thing.
No, I don't think that was.
No, not that.
Should I review the AMPS 2, 3?
Yeah, please do. Please do. Please do.
The question is the following. So let me go. Oh, you're going to ask me. I thought you asked me. I thought you said what question is
Hello. The question is that, so just now there was some discussion on complementary, etc., etc. So, so either this equivalence or quantum mechanics should break down. There is some kind of argument like that. So you are kind of saying that one particle quantum mechanics actually breaks down, but when you look at, but we are not supposed to do the one particle quantum mechanics. We should do the n particle quantum mechanics, and that is unitary. Right. So why do we, how the bulk unitary means what is happening in the bulk? So bulk also we shouldn't expect that this one particle quantum mechanics to be unitary at some level. So if you take the bulk and you look at some hypersurface, etc., and look at the evolution of one single particle. No, one quantum field theory actually means that one field. But this bulk fields will actually somehow get inside the horizon is getting entangled with the black hole degrees of freedom. So somehow that is lacking in this picture. So. But you are saying that small correction can fix it.
We say small corrections can fix it with the important caveat that you get this picture of local operators, the definition of local operators depends on this state.
No, okay, that I agree. That I agree. But I haven't understood the first claim that small correction cannot change it. Why this claim? No, not strong additivity. Even before that.
It comes from here. So think of this base curve. You can actually make a good case that the base curve is sharp. This is SE. This is time. So this is the entanglement entropy of the radiation outside. If you like, I can think of it as the entanglement entropy of some number of spins. Or I can think of it, if you remember the picture, there was a P tilde and let me call this C. I like to call this C. I'm sorry for there are lots of radiation here. A is the radiation that was emitted far away. So there's a black hole which is radiating. There's a lot of radiation that has been emitted which is called E. This is the black hole. And there's a pair being created at this point, which is the pair B which is falling out and the pair C which is going in. So is this notation here? Is that good? This is the setup. A is old radiation. E is what's called E. I can make it easier. I can make it. C is B. So A is equal to, so this is SE. Look at SE, it starts from 0, it ends at 0. It's a B.
So what are you calculating? Entanglement entropy of what?
I'm calculating SE, which is the entropy of the radiation emitted. What are the subtleties that are shown points?
Okay.
So I'm assuming that somehow I can think of it. In ADS-CFT, I really can. I have a plasma ball, I have some emission of, blue balls, so I really localize those blue balls and everything. It has this behavior.
Yeah.
Think of an old black hole, which is here, on this part. We have the following statements. SEB tilde, SEB is smaller than SE. So you are on this part of the curve. So after some time, B is going to go and join E. So you're going to move further down the curve. So you have the statement SEB is smaller than SE. It comes from unitarity. You have the statement SEB tilde equal to 0.
Initially 0.
SEB tilde is equal to 0 at all points, always, which is the statement of equivalence, principle of equivalence, or no term. This is the statement that B and B tilde are entangled, maximally entangled. Which is just a statement that these guys are thrown. Individually they are thrown. This is Hawking's computation. Okay, these three statements are in contradiction with strong subadditivity, which can be written in the form SEC plus S. This is clearly violated. Not only is it violated, it's violated by an order 1 amount. For the following reason, SBB tilde is 0, SEB is greater than SE, SB tilde is greater than 0, but it's not greater than 0 by a small amount.
So
It's
can you
greater
please
than 0 by a
explain
small amount.
what is SB?
SB is the entropy of the radiation. B is just one phase distinction.
So
B is one phase distinction. B tilde is one Hawking quanta.
Hawking-
Going inside,
sir,
B is one Hawking quanta is going
so
outside.
what is meant by entropy of one Hawking
So
quanta?
that's probably log 2 or something. It's think of spins being so in that case, SB is log 2.
Means is the maximum information that one quanta can
If it's
carry?
normal, yeah, then it will be log 2. If you want to think, you can think of this in terms of modes, in which case you might get some beta dependent factor.
Depending on the whole state, SB can be anywhere between 0 and 1.
It can be anywhere between 0 and 1.
If it's a product state, then it's 0.
Definitely.
Okay.
But in general, Hawking tells you that it's close to log 2. It's a and it's different from 0 by an order 1.
Yeah.
So this is the statement that small corrections can't fix it because this inequality is violated by an order of 1 amount. So small corrections can't fix the Hawking computation. This is the
And what can be the source of big corrections?
the firewall is one source of big correction.
Without
Firewall,
going-
firewall. I mean, actually, if you give this up, then you end up with this. It's very hard.
Yeah, fastball can another way. Yeah, that's what I'm saying.
Yeah, the first one doesn't work actually. There's so
Why
many
doesn't work?
corrections is you give up this. Because both Mathur and AMPS want to say you give up this.
You really
Okay.
If you give this up, you don't even have Hawking radius.
Yeah, so they want to preserve Hawking radiation while giving this up.
They have some convolute.
There's some argument to preserve Hawking radiation, you do some Euclidean something, and you get Hawking radiation.
Oh,
So they want to see if you can just behind the horizon and outside. I agree.
this of space, when you are falling in the black hole, you are not actually seeing one, not seeing one microstate. What happens when you're interacting with
Incorrect because it assumes that the statement is that it's a high energy observer who doesn't see a difference. Low energy observers will see the difference. So there's some argument of that kind. Initially that was now, which is that if you put in a high enough energy quantity, doesn't see it, but a low energy observer will see a difference. But that's not true. I think if you take any microstate in the CFT and you ask for an experiment, one correlation function somewhere here and somewhere here, which is a low energy correlation function because it's correlators across the size of the black hole horizon. So they correlated at the order of the temperature beta. I think the CFT tells you that these correlators should also be the same in any microstate. You can make a pretty good estimate and they should be very close to each other in any given microstate. So I don't think it's true that low, that low energy.
Sorry, so what is this saying? So you
So
have
there's
2
one
points.
statement which was made in the early papers, which I think now is at least being defined, which was that low energy observables will see a difference between different microstates, but high energy observables won't, which is I think what Mathur is referring to.
I see.
When you go in, so if a high energy observer falls into the black hole, he actually excites the black hole and you have to take that gravitation.
This is high and low compared to Hawking temperature, right?
Is that right?
Yeah, that's true.
So low energy observers see the difference between different Pascal
No,
geometries.
they do not, but because even if it's low, the password, the difference between the geometry somehow in this picture equals minus n or something
Then
like
who
that.
sees the difference between geometries?
No, it is not, you have to be very low. This of the order of exponential of minus n or something.
This I have not seen.
That is somehow.
Yeah. But see, then the point is, there should be a dual description where is described by smooth geometry, right? Pascal may be some description which nobody sees, right? Some mathematical description, but then the correct way to describe it, we need to find the dual description where it actually looks smooth, right?
Yeah,
And then all these puzzles will come back again in that description. See, the same problem I have here. For example, the Mathur says that if there is a very highly degenerate Hilbert space, then it will somehow appear as a smooth geometry, right? Yes. Now this weakly coupled D1, D5 system also has a highly degenerate Hilbert space. Sure. Here we certainly know that when you hit a deep end, you are not going to see a smooth geometry, right? So the existence of large degeneracy does not really mean that you should see smooth geometry, right? It's a very special case, right? That in this case, we know that a strong coupling is described by dual geometry, and only then you see smooth geometry, right? So to argue that we see a smooth geometry, we need a smooth description, right? Which the Husball picture tries to give up, right? I mean, it says that there is no smooth description in any way, right? I mean, if there is any smooth description, right, then we should use that one. So that's a relevant description for this problem, right? And we have to solve all these puzzles in that description.
Can I say something? So also the fact that you have a very nice formula for the entropy in terms of the horizon area, it may be to leading order, but then other people, Ashok, etc., have also computed, corrections, and it's a very solid theory actually of the calculation of black hole entropy.
And in Husball, you will give that up completely.
Completely. So then.
And it's the smooth geometry with corrections that are giving all the subleading.
Absolutely, yeah. Highly quantum stuff actually.
About the C modes, I mean, if I'm even within the CFT, which can describe the outside of the horizon, shouldn't I look for some degrees of freedom? Should I look for some degrees of freedom which are just getting infinitely slowed down and just hanging somewhere? There is a So I have the outgoing mode, so that's clear what it does. It just comes out into the far thing. And some guys which are just, right, because from the point of view of the Minkowski, from the point of view of the Schwarzschild time, okay, these guys are never going in, but I know what the C modes are. They are the ones which are sticking to the horizon. So if by cranking up strong coupling,
What is C mode? I'm sorry, these are the modes inside the horizon. B tilde mode.
B tilde modes. Yeah, the
take them to the definite frequency as far as the killing vectors. Let's say we are doing the time dependence has died out. So
Yeah.
the approximate killing vector, we take them to be of some definite eigenvalue of that killing vector. And then we want to seek a CFT interpretation.
Yeah, but those guys, isn't it true that they are just, so of course this is in the bulk description, they are just sticking to R equal to 2m and they're...
Behind the horizon, and I can take them to also be the ones that are following it.
No, but I can draw my, the Hilbert space of the C's just on a stretched horizon, at an epsilon distance thing. So then these guys are sort of about to go in. And I agree that this discussion I cannot make exactly at R equal to 2m, but let's say at R equal to 2m plus
These are the
epsilon.
ones that are coming from the other side. They're not the ones that are just about to go in. They're the ones that are coming from the other side.
But actually that distinction is I think important because let's say we start by taking a node inside
Yeah.
and asking we want an image of that, right? If you try to retrace it back to the boundary, then you actually encounter this Transplanckian problem, because
The mode inside.
yeah, the mode is inside. Because when they cross, they will encounter this collapsing matter, and there'll be a
Not only that, you encounter Transplanckian problem. It's a really ill-defined thing because if you give me some set of C modes and after some time I throw some matter in, after a time which is of order the scrambling time, the effective description of C modes will have been completely changed. Correlators on one side of the horizon and the other side of the horizon are completely upset by throwing in a little bit of matter because it's the same thing. Yeah, I think so. And you can compute that after a time of order the scrambling time, you perturb the system a little bit, and the old correlations you had are completely gone, and some new correlations have come up. So it's very tricky to evolve these
I
things.
mean, let me just understand. Suppose you threw in, suppose you had a black hole to begin with, you threw in a spherically symmetric shell of matter. So of course the mass changes, and also when it's changing, is that the
No, I think it's what you're saying. Now let's say you wait for time of order log x, which is the scrambling time, and now you look at modes that are just behind the horizon. Those are modes that at the time you threw in the matter were already very highly boosted, because otherwise they wouldn't have lifted the matter.
Yes.
So those are modes that have already interacted, a lot with the horizon. And so, you get a Transplanckian problem again.
Oh,
Then it's waiting for log
the
x.
stuff you threw in later.
Trace them all the way back for this reason. I think there's an operational definition of this. This is the following definition, I think. You want operators that have the following property.
So do you want to take the mic?
I can use the other mic. Mathur and so on are giving us the following challenge. It's the challenge of finding the following operators. Maybe I can, what should I raise? Actually, I think we have a pretty good description of these modes, B modes, in terms of CFT operators. So there is some mode n omega which I can write in terms of the CFT modes. Corresponding to these modes, there are some modes A omega and A omega dagger. And all these operators, n omega, A omega, and A omega dagger, n omega is of course equal to A omega dagger, A omega, have a good description, I think, in terms of CFT variables. I can write down an explicit map if you like, to leading order in one band. What Polchinski and Mathur and so on are saying is find for me some modes n omega tilde, A omega tilde, and A omega dagger tilde, which have the following properties. That the coefficient of correlation between n omega and n omega tilde is 1. Well, I was just calling the annihilation and creation operator. A tilde is annihilation and creation operators for B tilde, guys, behind the modes. So that n omega and n omega tilde are perfectly correlated. So you measure in a given state, you measure n omega, you get a certain result, you have to get the same result for n omega tilde, and all these three guys commute. Find for me such operators. And it's just this question, I think. And I think they've made a, I think you can argue that there are no state-independent operators of this kind, but there are state-dependent operators of this kind.
Sorry, I'm really sorry. So tildes are moved inside?
Yeah, and now the challenge is find, so I give you a state of the CFT psi, find an operator, which are the modes inside, so that it's perfectly correlated with the operator outside, n omega operator outside, and it commutes with the creation and annihilation operators outside.
Perfectly correlated, so no drama.
No drama, and it commutes so that you have some effective notion of locality. Now there are many such frequencies. So actually, let me put an omega prime.
What is the statement that you can't find? You said something, sorry.
So there are many such frequencies, a omega and a omega, and you have to find some set of operators that commute with all the frequencies. But these.
You'll be happy if it commutes with all but one.
You'll be happy if it commutes with all but one. But these guys already are forming a complete basis of the Hilbert space. So you have to find a second set of operators which also form a basis of the Hilbert space and which are correlated with the initial basis. So the question is, I give you a set of operators which form a complete basis of the Hilbert space. Now find for me another set of operators which also form a complete basis which have mutually small commutators. And that's actually not as easy as it.
It's only the inside. It may be some part of it.
It's a large part of the Hilbert space. I think if you think of the black hole after the page time, when most of the matter has evaporated into a gas of gravitons, in that case, the state of the black hole the state of the theory can almost completely be formed by taking the vacuum and acting with A omega dagger operators. So it's, yeah, A omega dagger.
The A tildes might be a smaller set.
Well, the A tildes have to have a A tildes have to partner all the A's. So every A has to have a partner A tilde, which better commute with things.
That's what is confusing for me. It is clear that there is a partner for every omega because with the black. If the interior of the black hole is small, I would think that.
Okay, it could be that there's only the problem is, I think that if you don't have a partner for every A omega and you try and compute the stress tensor as you so you could ask why is it you write down a local field operator in terms of you do an expansion in terms of A omegas and you write down a field operator on this side which involves also the A tilde omegas. You can actually compute this 2-point correlation function and you can ask why is it regular across the horizon. Actually, one reason it's regular is because you can take these A omega and A tilde omega modes and reorganize them into Kruskal combinations. But to reorganize them into Kruskal combinations, you need a partner for every omega. If some of the omegas are missing a partner, you'll get a divergence for a correlation function across the horizon. Because the Kruskal combinations pair up an A with an A tilde. For each omega, you have an A tilde. So unless you can get the right Kruskal combinations, it will be difficult.
Can I suggest?
Yeah.
Can I suggest a way out of this?
Yes.
See, it's possible that you cannot create A tilde omega dagger acting on the vacuum inside, independent of also creating A omega dagger.
That's what Mathur was trying to argue, right? In his
Silverstein was trying to argue this.
Because Mathur's other model also has something like this. That if image, that if create the particle but also its image. That if you try to create the image other than the particle, it costs a lot more energy. Yeah. And you basically go out of the Hilbert.
But it will be very difficult to write. You see, you have to write down an effective field theory that has these features.
But somehow they are violating the spirit of complementarity itself, I feel, by demanding that A omegas have one image and A omega tildes have another image. That is to say, okay, suppose you would always have to create A omega tilde with
Hilbert space. They are not acting in different Hilbert spaces. They are acting in one Hilbert space. So that's within the spirit of complementarity. If you now say that, you'll have to give me a reason why I can't do that. Why is it that some observer going in can't excite some of the A tilde omega modes, while that observer still sees effective field theory, but for some reason can't make this excitation of the A tilde modes?
So I would say that if that state could arise from the collapse of non-singular initial data, it's a legitimate state. But it's unclear if you just, suppose you take a state which has arisen from non-singular data column, and you now excite A omega tilde dagger on that state. It's unclear you could actually get it from non-singular data.
Let me phrase the problem this way. In order to preserve effective field theory, I want a description of local operators on this side of the horizon, phi of x, and operators on this side of the horizon, phi of y, some operators that behave like local fields. This is not necessary to have an effective field theory description, but I should be able to think of some such operators whose correlators I can measure. So I can have an observer who falls in and turns on some sources and measures something that corresponds to these correlators, phi of x, phi of y. If you want to construct any such operators that behave approximately like local operators, you will need A tilde operators to act autonomously on the Hilbert space. Now this is not, it's not necessary. Maybe you can have a description of effective field theory without allowing, somebody to excite phi and phi tilde even approximately independently. But you'll have to work hard to do that.
I want to do that, but the images on the boundary are only for those states which are legitimate, as in they can actually form. To demand that a state which cannot form should have an image is
Now,
too much.
here's how the state will form. I have an observer, I'll jump in and I'll excite a phi mode. I'll turn on a source for phi.
You will change the Hilbert space because you will increase your mass and so on.
So then you'll have to say that the,
Let me
yeah,
not
you can
it
do that.
like To argue
You can do that,
contrary,
yeah.
If I just have a state to begin with which forms from non-singular data, and I take another state where A omega dagger tilde is excited above.
No, there are no such states. I agree with you. You wait long enough, all these states fall into the horizon. So there are no states where A tilde omega is excited in addition to that state, as you say.
No, it could be, but you
Okay.
decide whether or not you have to see whether the state could form from non-singular data, and that is very complicated question because the Transplanckian effect will come in.
So I think you have to allow me to throw in infalling observers who can do experiments.
Okay, yes, I allow you. But is
So
there
then I go in and I excite A tilde omega. You have to tell me why I can't excite it. You could say that, when I go in, and some people say this, this is one of the resolutions. There's no interior independently of an observer who jumps in to form the interior. So, when the observer jumps in, he extends the Hilbert space a little bit, and then he can create some A tilde modes because he has himself jumped in and entangled the thing with some other. You could do that, but that's the resolution you're proposing.
No, I'm proposing that the guy you threw in
Yes.
in conjunction with exciting A omega tilde is okay.
Yes.
But without that is not okay. That is, not every operator you will try to write down an effective field here. You need to have a boundary to it.
But-
there's some set of
So describe the following experiment for me. I have a person who jumps in, who turns on a source that couples to A tilde omega. And he measures some correlation function, some of which make reference to the A tilde omega, and I want a boundary description of that thing. So if you don't have a boundary operator for A tilde omega, how will you describe that? I think what you're saying might well be right. It may be the right answer, but it requires some, Sorry, let me ask a very elementary further. What do you mean by this bracket? I mean, is it a simultaneous time? I mean, I don't understand the time relation between outside and inside. In the commutation relation, you fix time, right? No. I don't have to fix. These are not local operators. No, not local operators. These are Fourier transforms of local operators.
So these are not equal time.
Well, they're not equal time commute. I could make them, but right now I'd Fourier transform them already with respect to something. So then they evolve in some very trivial way under time evolution. This goes to e to the I omega t, and this goes to e to the I omega prime t.
So for this,
The time inside is not careful.
So one of them evolves with the opposite time. A tilde omega has energy minus omega or something. Even here, I think, but it depends on how you define A tilde omega. But if I define it with respect to the same killing vector, then I think.
okay, so let's see. So the infalling observer, right, and this ingoing quantum, they differ in some way, right? They are different in their momentum direction.
The infalling observer and the ingoing
What
quantum.
is the ingoing quantum? What is the difference? The infalling observer increases mass, whereas the infalling quantum decreases mass, right?
Right. So the what you think of as the creation operator for the what I'm calling A tilde omega here does indeed have negative energy. viewed from some asymptotic, from some
But
asymptotic.
from the infalling observer viewpoint, what is the difference? It's not a negative momentum, right?
The infalling observer is actually an excitation of the A omegas to start with, the ordinary guys. You see, if you think of a field expansion behind this, then there's the ordinary operators and the A tilde omega operators. The A tilde omega operators are the ones I think that have the opposite. They're coming from the other side. I think they have the opposite energy.
And infalling observer, you are saying just A.
I think it just stays. He can later turn into some of the A tildes through interaction. So he can, through a phi cubed interaction, he might gradually get transformed into the A tildes. But I think he starts off by just being A's.
So all the modes available to the infalling observer are the A's.
I think so.
So you have to create an A field and
I think so. By an interaction, a 5 to the 4 interaction would create it.
modes are on the outside of the
Yes, yes, yes.
So as he falls in, his description, I mean, we will have to do, what's the question? We are trying to describe the infalling observer inside the horizon, but contrast him with the A tilde, right? So, I think A omega affects a mode which is moving upward along the horizon. There are also modes moving, which are infalling, the V modes or something.
Right,
And then the infalling observer is outside, made out of the V modes,
Probably that's right.
which then continue nicely
Probably, that's
outside.
right. So A omega plus e to the minus beta omega into A minus omega. Yeah, that's probably right.
yeah,
Maybe
so
you
if
should use those
do
modes.
geometric picture, then in this picture the Gautam group, right? It's like very
Maybe,
interesting.
yeah,
Coordinate
yeah.
one is going like this, that is the infalling observer, and the ingoing quanta are like this. Right? And now you are trying to create those ingoing quanta from this infalling observer.
Yes, yes.
So what does it take to do that? I mean, is it a
Should be able to turn on sources that couple to the fields. So if I have some source J that couples to my field phi, I'll turn on all sorts of quanta. So if my infalling observer carries a small, magnetic field or something that couples to a scalar field, I can turn on, or charge, just a charge will turn on all these modes.
Now, but Ashok's point is right. Insofar as one is left going and you're trying to create right going modes,
But it's not a free field theory.
it's not a free field theory, but you have concepts and you will have to do your proof.
I think you can create right moving modes. A mass will couple the two. So just a
phi, of course, you are assuming massless. The quanta that you are trying to excite is massless, right?
It doesn't have to be massless. No, that's just simplicity.
Well, if it's not, I mean, this contradiction probably arises from massless modes, right? I mean,
No,
for massive modes, it will be like the emission rate will be exponentially suppressed. Right?
Okay, I can turn on a very small mass, so the black hole temperatures.
Well, if it's a very small mass, then I mean, amplitude of exciting these other modes will also be very, very small.
Okay, I agree. I mean, I think it's very unlikely you won't be able to excite the right moving modes at all. You can do something and excite the right moving modes. It seems there's some loop effect. Something will do it. Something that's not suppressed by Newton's constant. The standard model you can still excite. Yeah.
Is it possible that this A's and A tildes basically are built up of some other than microscopic fields?
Yes. Yes.
I raise this because if you look in the ABS-CFD correspondence,
Yes.
we know that a black hole corresponds to a thermal state.
Yes.
And no black hole is zero temperature.
Yes.
Always zero. But all the operators of the thermal state or the timing space
Yes.
are all built up of gauge fields
Yes.
in different combinations.
Yes.
In one case, you have these local F squares and their derivatives, etc. You create gluons. Inside, you have the gluons, or you have these long winding strings and stuff like that. So clearly, the operators that describe the deconfinement phase and the confinement phase are very different, but they are all made up of gauge fields.
Very, very.
So I would imagine, I mean, this is a plasma ball picture. If you take a dual of this, I have a pretty good dictionary for blue ball to graviton.
Lack of left reverse. That's the following argument. As we've been discussing so far, these. Let me think of the A tilde A dagger omega mode inside. This A dagger omega mode actually has negative energy with respect to the CFT. So actually, H A dagger is minus A omega dagger. Even though this is not the natural infalling mode, that may be some, but actually it has negative energy with respect to the asymptotic Hamiltonian. However, tilde. However, it satisfies the same algebra. Okay, I'm going to drop delta functions and write it this way. I hope you'll excuse me. Okay. Now, this looks like it's a problem because it says that is equal to 1 plus, sorry, I made the wrong mistake, sorry. Tilde omega is equal to 1 plus, now this actually tells me that A dagger omega has a left inverse, which is A, A tilde omega in by 1 plus, this is a positive operator, so I can do this. So A tilde omega dagger has a left inverse. But this is a problem because A tilde omega dagger in the CFT is an operator that maps states of higher energy to states of lower energy. But there are fewer states at lower energy than there are at higher energy because the entropy is a monotonically increasing function of energy. So any such operator which maps states of higher energy to lower energy doesn't have a left inverse. But here you see that this operator A dagger omega, if it satisfies the right algebra, has to have a left inverse. So no such collective excitation that you can find will have a left inverse. So I'm playing the devil's advocate here, but yes. This is the argument against any such map you might like to find, but very complicated map between gluons and so on and these A tilde omega modes.
And this is not affected by small correction?
I think not. It's just a statement that has to be a left inverse.
So even if it's not 1, not exactly 1.
Yeah. Yeah. Right.
Sorry, I can you said the challenge was to find out a mode which will satisfy R is equal to 1, right? For the eternal black hole, what is
For the eternal black hole, these guys are not living in the same Hilbert space.
Yeah, they are part.
A omegas span only half the Hilbert space. Then you can clearly do it.
What if this relation holds for some of the states, but
that's our resolution. So our resolution is that these operators A tilde omega have the property that this is true. Psi is equal to psi, or between some given set of states is equal to psi phi. But I'm going to restrict for you the number of states you're allowed to explore at one time. So you give me a semi-classical geometry which corresponds to some state psi, and of course you can explore states that are close to this state psi which correspond to phi by making excitations. But the operator A tilde depends on which geometry you're talking about. So for every geometry I'll give you an operator, in which case this relation holds not as an operator relation but within states. If it holds within states, then there's no contradiction. So this is within a state phi, within a state psi and some states phi. And if I go to a state that's very far away that corresponds to a different geometry and a different microstate, then this relation doesn't hold. So that's exactly the resolution. That if you allow these state dependent maps, then you can indeed you can have this algebra being obeyed to a very good approximation to any experiment you can do, but it's not really obeyed as an operator relation in some abstract space. I think.
But let me ask you this. I mean, aren't you sort of trying to, let's say we identify the operator A tilde just to play devil's advocate, in a particular state.
Yes.
Okay? You start with a particular state, it has an interior, you identify an operator A tilde.
Yes.
Now, once you identify it in the CFT, it's some operator, trace F square plus whatever, some operator. Okay, you can certainly study the action of this operator in any state.
Yes. Yes.
Right. So take another state, if you like, not very close by, and study the action of that operator in this other state. You are saying this commutator won't be 1.
This commutator won't be 1, and this operator is not what the infalling operator observer will interpret as A tilde in that other state.
So that's what I was coming to. But on the other hand, isn't it true that for low point correlators, most states can be well described by geometry? You yourself said.
I think that's true, but it's.
So then, if most states can be well described by geometry, there should be a tilde operator for the other.
There is an a tilde operator, but that's not the same as a tilde operator. So I'm saying
entire one. What is it? In many parameter family of such operators satisfying this algebra.
So you have many parameter family satisfying this algebra.
But isn't that a bit strange?
No, because I think in a given state, you can select which operator you have.
Oh, I see.
So in a given state, you're restricted to one operator. If you go very far away, you have to use a different kind of operator. It's not so surprising. This is actually very conventional in a certain sense. It's a statement that you can't have background independent local operators in a quantum field theory. Now, if instead of talking of a tilde, if I start talking about phi of x, the field phi of x, what does phi of x mean? How do you even specify the coordinate x independent of the geometry? So it's the statement. So this is really where the issue is. In a very naive sense, I would say when I excite this, I'm exciting some phonon modes. But the existence of the phonon modes has to do with the existence of the table in the first place. So the phonon modes exist as some effective excitations around some coherent state solution of some field. They don't exist in general. So the statement that the operators you're using are state dependent in that sense, and in quantum gravity have to be state dependent, is in some sense part of standard lore. You can't even localize an operator without giving me a geometry.
In fact, let me just give you some, this kind of a thing,
Yes.
it's actually well known in case of Fermi seas.
Yes.
Near the Fermi surface, if you take a particle hole operator and
Yes.
call that A,
Yes.
so of course A comma A dagger
Yes.
is not 1.
Yes.
It's another particle hole operator.
Yes. Yes.
The point is that, if you take the states phi
Yes.
to be in a certain band of this thing, then the expectation value of whatever junk appears on the right hand side, okay, that actually becomes 1.
Right. Right.
Okay, so that's a well known thing, of course.
Yes.
But now I'm saying that it could very well be that if the Fermi surface is like, undulating or something like that, then your construction of A in terms of psi dagger psi could also be different. For example, for translational invariant systems,
Yes.
the A in terms of psi dagger psi is something,
Yes.
and for something which is a weight,
Yes.
it could be
Yes.
something else.
Yes. Let me play devil's advocate a little more and tell you what Polchinski and Marolf have to say about this. What Polchinski and Marolf say about this and about Gautam's construction is, okay, very good, but actually in this Fermi C's case, we can do the following. I can write down an operator that looks like AI into PI. So PI is for flat Fermi C, where PI projects onto flat Fermi surface, or whatever, sorry, whatever, a normal spherical Fermi surface, okay. Okay, plus AI prime into P, whatever elliptical Fermi surface, or whatever Fermi surface, into some other shape. So I can project onto whatever particular Fermi surface I write, and write down an operator of this kind, which reduces to the correct operator in any given state. So this is the kind of thing you actually can't do for the operators you're constructing. You can't write it in terms of, so it's the same operator, which looks like it's a different operator effectively, but is not actually a different operator. The electron is the electron, for sure. But
Electron is electron, but the collective excitation is written differently in terms of this electron.
so they, yeah.
Microscopic degrees of freedom are the same.
That's right, but the effective degrees of freedom may not be the same.
Yes.
But Polchinski and Marolf would try to say you write down one map between the microscopic degrees of freedom and the effective degrees of freedom, so that the map has the right limits. You go to a particular limit and it becomes the right map. You go to some other limit, it becomes the right map there. So that is the kind of thing they would like to do even in quantum gravity. Actually, for a Fermi surface, you probably can do.
May have no nice property.
May have no?
An operator like this may have no nice property at all.
So they want to write down a map which does have the property that reduces to the right thing in the right microscope. What will have the right algebra? I think you can't write down an operator of this kind. These operators I mentioned, I think you can't write them in that form.
Yeah, I mean, while it have different terms will all commute, or is that one?
Yeah, here different terms will all commute.
It will
Yes, the projection of.
projections will be the identity. That's why I was thinking
But you can't write this operator in that form. For this, I mean, I think then you're subject to these arguments. You have to really write down something that doesn't, that is state dependent. And in quantum gravity, it's possible because when you say phi of x, what does it mean? They want to say that
must be a spherical partition or vice versa, right? So why should they come with?
Okay, so I'm still playing the devil's advocate. I don't have a good answer for this, but
I also don't understand this construction. I mean, you know, like I can have psi dagger n, psi n minus n, summation over all n for the flat Fermi surface, and I can have some weird other thing, and I don't see how.
Sorry, my thing there is my construction is very schematic. The question is really the objection in principle is, can you have independent operator, just one operator in the CFT, very complicated operator, state independent, that reduces to right limits. You don't have to take that seriously. That's extremely schematic. And if you can or if you can't. I think if you can, if you insist that you have to, then I think it's all these arguments hold. And I think if you insist, if you are willing to give that up, then I think they don't hold. Maybe we should talk about some of the other things. You want to talk?
No, actually I don't have time. No, actually, one of the things I would have talked about is Mathur and Susskind and flat space anyway. So please go ahead. That would be great. That was
No, why don't you speak about it? You can talk about it.
Number 4, is it possible to say very simply?
Yeah, I can say number 4.
Will you tell the Marolf Polchinski?
Yeah, that's number 4.
Yeah, that's important.
So number 4 is the following argument. Number 4 is the argument that think of a given state psi in the CFT, and let me sorry. Okay, so there's the operator which I'll call n b omega, which is in the notation I've been writing, it's a omega, a dagger omega into a dagger. This is the operator n b omega, which measures the number operator of the. Now the leading order in 1 by n, this guy commutes with the Hamiltonian. Okay, 0. Now, good. Now now they say in a given, let's say you take a given eigenstate of this number operator. A given eigenstate of this number operator, in fact, doesn't have a smooth geometric description. Okay? But typically, such an eigenstate will not have, nb omega will not, the eigenvalue will not be equal to that of nb tilde omega, where nb tilde omega is equal to a omega b tilde a omega dagger. So typically, in an eigenstate of nb omega, the eigenvalue of nb omega will not be equal to the eigenvalue of nb tilde omega. Okay. Nb tilde omega is this in terms of these operators we've been talking about. Good. Now they say, well, consider, let's consider the occupation. So there are 3 operators I'm going to introduce. I'm now also going to introduce the operator NA, where NA is the occupation number observed by the infalling observer. So this is given in terms of these operators by, a omega plus e to the minus beta omega into a tilde omega dagger into its conjugate times CH, something like that. So it's number as seen by the infalling observer. Okay. Now they say, well, hence because the typical eigenstate of this will not have the same eigenvalue for this guy. A typical eigenstate of this will also have an expectation value for NA that's non-zero. So in a typical eigenstate of NB, the expectation value of NA will be non-zero. Now let's say we are doing a microcanonical, we're trying to evaluate the microcanonical average of NA. So in some states of in a given energy band. Now because we have this relation that NB commutes with E, instead of doing the trace in some energy basis, let me do the trace in some basis of NBs. So every given, there might be some 1 by n corrections. So in the end, every given energy eigenstate is some very complicated linear combination of the NBs, of the NB eigenstates. But I can do a change of basis so that I can do the sum in the NB, the trace in the NB eigenbasis. And they have an estimate for how much of a spread of energies you need to take, which they say has to be much larger in the temperature or something. Fine. Now in any given NB eigenstate, they say, well, typically the eigenvalue of NA will not be 0. And this is a positive number. So in the microcanonical ensemble, the expectation value of NA is not equal to 0. So this is the statement that the infalling observer encounters particles. So there's a firewall.
Because you can do it mode by mode.
Right, because you can do it mode by mode. Now there are 2 ways out. So Polchinski will say, well, maybe the operator NA doesn't exist because the operator A tilde omega doesn't exist. You could say that. or Marolf will say, well, it exists, but there's a firewall. We would say actually that the operator Na is again state dependent. So in doing this microcanonical trace over different energy bases, the operator Na is changing as you do that. So you can't do a change of basis because when you're taking the trace, the operator you're tracing over is actually changing as you're changing the basis. So then, in that case, this argument is invalid. And in fact, in the construction, the construction is designed to give you Na equal to 0. Yes.
So I didn't quite follow this argument. Can you just repeat it again?
Okay. The Polchinski argument.
Yeah.
Once again. Okay. So the claim is that let me think of.
The boundary really makes it more legitimate, but it does go back and forth.
It goes back and forth, but I think this mapping at one band we understand well. So we understand the mapping between the A omega modes in terms of the boundary modes. They're saying, well, let's say you demand that there is some similar mapping. So the question is always about this way. Okay, so let me try and say it again. So let's say a typical energy eigenstate in some is given in an energy eigenstate has some expansion in terms of NB eigenstates.
So you are now working on ADS, is it?
I'm now working on ADS, but as Sandeep says, I'll go back and forth between the bulk and the boundary.
And ADS in global coordinates?
Let me work in the Poincare path so I can talk about these omega operators. So I can work in global coordinates also, but let me so I can talk about momentum operators. Okay. So generally, some energy eigenstate is given by some of coefficients in B into some other in BO, some A. Okay, so it's some linear combination of things of this sort, of eigenstates of NB and eigenstates of some other operators. Okay, good. But in fact, okay, and now
These are the modes outside. These are the modes outside.
these are the modes outside. Good. Now they say, well, let's say we are doing a microcanonical trace over of this operator Na. We might just as well do it in states of definite NB. Okay. Now, why is this allowed? You could try and repeat the same argument in Rindler versus Minkowski, and hence come up with the argument, the result that in Minkowski space also the infalling observer sees something. That's not true. And the reason it's not true there is because, NB doesn't commute with the Hamiltonian. If I take a state of a given NB, that's a state of a very high energy. It's really a state of a firewall. Okay? But in the CFT, since we have a good CFT description of NB, it looks like NB does commute with the Hamiltonian. So there's a reasonable chance that you might be able to do this trace in the NB basis. You can't do this in Rindler and Minkowski. And if you do the trace in the NB basis, and if you evaluate the expectation value of Na in the NB basis, so you make a change of basis, then in every individual state Na is not equal to 0. And since Na is a positive operator, it looks like it's not equal to 0 in the microcanonical ensemble. So I start off with doing a sum in the energy ensemble. I make a change of basis to this NB ensemble, which I can do because NB approximately commutes with H. And then I conclude that Na is not equal to 0. Is the mode seen by the infalling observer. So it's a number operator for some infalling modes. I may not have written this formula correctly, but it's something like this.
But an infalling observer has a boundary description, or that you don't use boundary description?
So if A tilde and A both have boundary descriptions, then the infalling observer has the same boundary description as is given by the Bogoliubov transform.
Is it an argument that the infalling observer doesn't have boundary description?
That's Polchinski's interpretation. So if you look at the conclusion of this paper, that has a very different statement from the abstract. The conclusions, yeah. Okay, no, that's right. No, they have very clearly different biases. Polchinski says very clearly A tilde omega doesn't have a boundary description, whereas Marolf says Na is not equal to 0. So you can take the conclusion to be either way.
But in any case, the issue is whether A tilde or A which is...
So, then you know A tilde. So this means either there is a firewall or there is a boundary description for it.
Yes. That's true of all the arguments they are giving. Every argument you can resolve in this way. Either there is no boundary description for the interior modes, A tilde, or there is.
Or either there is no description of the interior modes we found as yet, right?
Yes, I think these arguments persuade me actually that there is no state independent description. So I think I would actually move it forward to either you allow operators which depend on the microstate, or else you accept one of these two conclusions.
So then what is the objection you have to trying to say a similar thing that
I don't understand how to phrase the paradox in that. The mirror will in the end have to have complementarity.
The charges collect near the horizon, and then it is these charges which carry information about stuff inside.
But it sounds like a very complicated thing, because in the end you have to first realize black hole complementarity here. The image charge has to start depending on things that are far away. You see, you can't work in the limit where everything has gone far away, infinitely far away, because then information is lost. So somehow you have to realize black hole complementarity here. You also have to realize a system where you really have image charges, where you have set up. It seems to be unnecessarily complicated to me. I don't see actually any reason to not think of the spin chain and to think of that model. But
I don't know what the time situation is, but
yeah, but
this
10 minutes more.
idea
Yes.
of, state dependence, will you tell us more tomorrow?
Yeah, I'll talk about it tomorrow. Yeah. You want to talk about Malvicina sustain in flat space? I can. Maybe you should. You want to do it? I don't want to convert this into at 4, right? We have 5 minutes. Okay. So Malvicina Susskind, in my interpretation of Malvicina Susskind, which please is that one of the things they're doing is they're trying to geometrize this picture of complementarity. Of saying that it might be that the description of some degrees of freedom here is in terms of degrees of freedom very far away, without getting any observable violation of locality. So one way you can do that is by thinking of the eternal black hole in the following way. There's this Wheeler, I think, wormhole solution, which says you take two Schwarzschild black holes, which are initially on two separate sheets, and then you connect them very far away. So now you have a black hole here and you have a wormhole here. So there's a space-like sheet which is connected very far away. Okay? So now this is a multiply connected solution. To go from this point to this point, you can. So this is actually a space-like. So even though I've drawn it this way, I can draw it the other way if you like. You can go either from here, or you can go very far away and come back. Okay. So this is the kind of setup where the interior of. So for example, one of the setups you could have is you take this black hole, you allow it to evaporate, the radiation goes very far away, then you collapse it back into a black hole, and then you end up with this wormhole opening up here. So this is an example of where in flat space it looks like the interior degrees of freedom here are actually described also by the interior degrees of freedom here. Okay. But there's no violation of locality you can make. There's no way you can use this wormhole to send messages. So I think that's one of the answers they want, that's one of the points they wanted to make in flat space. So physically these things could be very far away, and it's very strange that two things that in physical space are very far away are actually connected in some sense. They're describing the same thing, but there's no way you can use this to get a violation of locality. If you throw a book in here, it comes out completely. There's no way you can throw a book in here and expect to read it in the other side.
If I might be a little different, had you not known about the bridge, the fact that you can fall in through the black hole horizon on the top and encounter a hot photon
Yes.
that was sent from below would have seemed like a violation of locality.
Fine.
But there's actually a bridge because of entanglement.
Okay. Okay. Okay.
Is the claim that anytime you have macroscopic entanglement, there is a bridge?
That seems to be the import of this equation, but it doesn't. Let me also give you the Polchinski-Marolf counter argument to this.
My conclusion there is that this tends to be specifically designed for uncharged black holes. Suppose you have two large black holes carrying large charge, right? They have large entropy and they can be maximal entangled. And here I don't see how you can form a macroscopic bridge, because typically you have to have opposite charges to form the bridge, right? The flux goes through one and then comes out to the other.
Yeah. Even in the uncharged case, it seems unlikely there'd be a bridge. Maybe that's right.
And in fact, it becomes more serious for supersymmetric black holes, where you want to expect, right? Because you expect a supersymmetric wormhole, right? Which will have it's a supersymmetric black holes typically carries almost same charge for the centers, right? Direct put black holes of opposite charge, right? It's not supersymmetric. So there I don't see how you can entangle. You can certainly imagine that you have two black hole system, right? Which is supersymmetric. Each carry large entropy, so they can be highly entangled, right? And I don't see how you can form a bridge between them.
Why do you have to send the lines of force through the? All the lines of force can connect Ah, I see. I see.
Because there's a source, right? So as you go into the horizon, the interior, you carry the flux with you. Okay? Normally, you don't talk about the other side, so the flux keeps going. Right?
Okay, so that's a very good point. But maybe they'll say it's enough for us that anything that can be pair produced, suitably is always entangled. And Hawking radiation is roughly speaking, a kind of pair production of the interior with the outside. I think it's too much, but it's little, we have this diagram, it's obviously suspect. Little wormholes are being created which are,
But I agree, but that was a microscopic wormhole. But I'm just saying that if the claim is that macroscopic entanglement tolerance can be thought of as macroscopic breaks, right? That seems too strong a statement.
So there's also this argument that Polchinski and Marolf have in the same paper against this interpretation of entanglement equaling wormholes. I can give you that argument. The argument is that if you think of this eternal geometry, so this I want to leave here. Let's say you think of this geometry. You compute the correlation function of some field here. This correlation function is some order 1 correlator. So the presence of the wormhole leads to, the fact that you have this smooth vacuum and you have a wormhole leads to correlations, non-trivial correlations between some observers measured here and some observers measured here, some operators measured here. Or it also leads to non-trivial correlations between some operators measured here and some operators measured here. Now they say, well, now let's say you do some, you look at some generic entangled state that has the same degree of entanglement, but where the entanglement is not conspired, is not conspiratorially done in the thermophile double way. And then they estimate the size of the correlator between an operator here and an operator here. And they find that for the generic entangled system, where each system has e to the s degrees of freedom, the size of the correlation function you'd expect would be e to the minus s. Whereas if you had some geometric wormhole that was connecting these two entangled systems, you'd expect that the correlator would be order 1, as it is in fact in this thermophile double case. So at least if you measure some electric field in one place and electric field in the other case, you'd expect to get correlator of order 1. But if I take these Hawking quanta and there's some generically entangled things, some collection of electrons and positrons is produced, and measure the electric field in one case and the other case, it looks like I'll get a correlation that is order e to the minus s. So that suggests that you can't have a wormhole in generic cases. The response to that is that this wormhole could be very long in generic cases, so you could get e to the minus s from the length of the wormhole bit. Right. Break for tea, okay. Are there any other things?